Sealed tomato packs are already moving down the line fast enough that each one disappears before you can fully register it. Their filled closed label. Finished. But nothing here is checking them. A stream of thick tomato pulp feeds into filling nozzles upstream perfectly, timed with empty containers arriving in sequence. The alignment looks precise until one container drifts slightly off position. The fill overshoots, then the system corrects, not by stopping, but by adjusting the next few fills. The line keeps moving. Sensors react in milliseconds, recalibrating volume, shifting timing. But every correction happens after the pulp has already passed through. What passes through isn't confirmed, it just hasn't been rejected yet, and the pace doesn't allow for reversal. At thousands of units per hour, there's no visible point where the system slows down to confirm what just went through. The faster it runs, the less opportunity there is to intervene, which creates a contradiction that doesn't resolve the system, looks tightly controlled, yet everything inside it is still waiting to be accepted somewhere else. And by the time each pack reaches the sealing stage, whatever was inside has already been locked in. So if nothing is being checked here, where was the decision actually made to understand that you have to move upstream before the system commits to anything it can't take back? Rows of sealed tomato packs slide past at a speed that barely leaves room to focus on a single unit. Each one looks identical, same color, same thickness, same label locked in place before it even reaches the end of the line. Nothing here suggests hesitation. The system doesn't pause. It doesn't ask questions. Yet every pack carries a quiet decision. A filling nozzle drops measured portions into containers in a steady rhythm, and the sealing heads close them almost instantly. There's no visible check between those two moments, no inspection that slows the flow. The line assumes something has already been decided upstream. The pace itself becomes the first pressure. If anything inside that stream is off temperature, consistency, contamination, there isn't an obvious place for correction here. The line keeps moving. A counter flashes briefly, thousands of units per hour. The number feels impressive, until the question shifts, how many of those were actually verified before they got sealed? Because at this point, by the time it's sealed, the system has already moved past the point where decisions are made. Just upstream, the containers aren't sealed yet. They arrive empty, spaced precisely, each one timed to meet a stream of thick tomato pulp flowing from a stainless steel pipe. The alignment has to be exact. A fraction too early or too late, and the fill drifts, overflows, or underfills, but the line doesn't stop to correct it. Instead, it adjusts. Sensors track volume in milliseconds. If a fill falls outside tolerance, it triggers a subtle correction, slightly slower flow, a brief shift in timing. But those corrections don't isolate one container. They keep the system running without confirming what's actually valid. The pressure here isn't just accuracy, it's synchronization. And there's a detail that doesn't quite resolve the system, reacts to what it measures, but only after the material has already moved. By the time a deviation is detected, it's already inside the container, or already past it. So the line keeps compensating, pushing small corrections downstream, which raises a problem that isn't visible. Yet, where do those accumulated adjustments finally get settled? Further back, the pulp itself is never still. It moves continuously through heated pipes, thickening as it travels. There's no pause between stages, no holding tank, where someone can stop the process and take a closer look. The system depends on motion. Temperature climbs gradually, controlled within a narrow band. Too low and the product won't concentrate properly. Too high and it begins to degrade. The margin is small, but the flow doesn't wait for confirmation, it keeps advancing. A valve shifts slightly, adjusting pressure. Another sensor registers viscosity. The system responds again, tuning itself in real time. It looks stable, it looks controlled, but there's a constraint hiding inside that movement. Once the pulp crosses a certain point in the line, it can be reversed, not cooled back, not diluted back, not separated again. The transformation becomes one-directional, and that creates a quiet tension because every adjustment now affects everything that follows. The system appears flexible, but the material itself is already committed to a path it can't leave. So corrections continue, but always after the fact. Before any of that controlled flow even begins, the system opens to something far less predictable. Truckloads of raw tomatoes arrive in bulk, uneven in size, mixed in ripeness, carrying dirt. Leaves sometimes damaged fruit, already starting to break down. They don't enter the line one by one. They drop in waves. Sorting belts spread them out, but not perfectly. Cameras scan for defects, color differences, irregular shapes, but the decisions happen fast, almost too fast to fully resolve what each tomato actually carries. Some are pushed aside, most continue forward. Then the washing drums take over. Water churns aggressively, lifting debris, rinsing surfaces. It looks thorough, almost final. But the pressure here isn't just cleaning, it's speed. The system cannot slow down to inspect every piece individually. And that creates a boundary. Whatever passes this stage is effectively accepted into the process. A bruised tomato slips through. A small contaminant isn't fully removed. Nothing dramatic happens. The line keeps moving. Because at this scale, the system doesn't eliminate variability, it filters just enough to keep going. The question stays open: how much of what gets through is actually clean enough? The answer doesn't come from the machines. Midway through the line, the flow slows. Not everywhere, just at a single station, where the pulp is briefly exposed before the next stage. A technician stands beside a narrow sampling port, pulling small amounts from the stream that has been moving uninterrupted until now. For the first time, the system pauses long enough to be judged. The sample is checked: viscosity, color, consistency, sometimes even smell. The machines around it continue running, but this moment interrupts their assumption of continuity. Because if this sample fails, everything behind it becomes uncertain. And when that happens, the line doesn't just adjust, it waits. A decision is made: accept, reject, or reprocess. Each option carries a different cost, but none are invisible. The flow that looked fully automated is suddenly dependent on a single human call, and that shifts the entire understanding of control. The machines move everything forward, but they don't decide what is allowed to continue. Once that decision is made, the effect doesn't stay in one place. If a batch is flagged for reprocessing, valves redirect the flow. Pipes that were feeding forward suddenly loop backward, sending material into holding tanks. The system doesn't stop, but it no longer moves cleanly in one direction. Buffers begin to fill. At first the change is subtle, a slight delay between stages, a minor imbalance in timing. But the line was built for continuous movement, not hesitation. As more material accumulates, the pressure shifts from processing to managing overflow. And then the slowdown becomes visible. Containers arrive faster than they can be filled. Pumps adjust, then adjust again. Some sections idle briefly, while others strain to keep up. The efficiency that once depended on constant motion starts to break apart. All of it traces back to that earlier checkpoint. A single rejection doesn't just remove product, it reshapes the flow behind, stretching timing, increasing load, forcing the system to compensate across multiple stages, which raises a deeper problem that isn't fully clear yet. How many of these small decisions can the system absorb before the entire line begins to lose pace? The slowdown doesn't stay isolated, it spreads sideways. From above, the factory no longer looks like a single line. It's a network, multiple stages running in parallel, each feeding into the next with precise timing. Sorting, heating, concentration, filling, sealing, they don't just follow each other, they depend on each other. And that dependency tightens under pressure. One section accelerates slightly to compensate for earlier delays. Another slows to avoid overflow. The system begins adjusting itself not globally but locally, each stage reacting to its neighbor. That's where the imbalance appears. A pump runs slightly ahead, building pressure in the line. A filler waits half a second too long, creating a gap that ripples backward. These aren't failures, they're small misalignments, but they stack, because no stage operates independently anymore. The system starts behaving less like a sequence and more like a web, where every adjustment pulls on something else. Efficiency isn't just about speed now. It's about alignment, and somewhere inside that web there has to be a point where everything becomes sensitive. The problem is it's not obvious where that point is. Step back further and the scale becomes harder to ignore. The line doesn't produce dozens of units, it produces thousands every hour without pause. Streams of pulp become streams of packaged product feeding directly into outbound conveyors that don't wait for inventory to catch up. At this level, timing isn't just important, it multiplies. A delay of a few seconds at one checkpoint doesn't stay small. It expands across the entire system. Containers miss their slots, pumps adjust flow rates, buffers fill faster than expected, and suddenly the output number starts to shift. Not dramatically at first, a slight drop in units per minute, then a wider gap. The system compensates, but each correction carries its own cost. More pressure upstream, more instability downstream. A display panel shows throughput figures, but it doesn't explain why they change. The numbers move, but the cause remains buried inside the line, which makes the real question less about how much the factory produces and more about how much depends on each single decision made along the way. Seen all at once, the system stops looking like a smooth flow. It becomes a sequence of decisions. Raw tomatoes enter with variability. Machines filter and transform them continuously. Flow carries everything forward faster than any single point can fully evaluate. And then at specific moments, the system pauses just enough for a human to decide what continues. That pattern repeats even when it isn't visible. Each checkpoint doesn't just inspect quality, it defines the path of everything downstream. Accept, and the system maintains its pace. Reject, and the system bends, redirects, slows, compensates. So control isn't distributed evenly across the machines, it's concentrated. The pumps move material, the heaters change it, the fillers package it, but none of them determine whether the system is operating correctly. They only execute what has already been allowed. The real control sits at those narrow points where the flow can be interrupted. And once the line moves past them, the outcome is already set, just scaled across thousands of units. At the end of the line, everything looks simple again. Finished tomato products stacked onto pallets, wrapped and labeled, ready to move out of the factory. Trucks are loaded continuously, feeding distribution networks that stretch far beyond the plant itself. The system doesn't stop. It doesn't reset between batches. It carries forward hour after hour, day after day. From the outside, it appears seamless, an uninterrupted flow, from raw harvest to packaged food on the market. No visible pauses, no visible decisions. But those decisions are still there. Every unit leaving the factory has passed through a chain of checkpoints, adjustments, and compensations. Some slowed the system, some redirected it, some allowed it to continue without interruption. None of them are visible here. What remains is the output, consistent, uniform, moving at scale. And behind that consistency is a system that only works because countless small decisions keep it aligned moment by moment, long before the product ever reaches the end.